Lists are usually trash. Most channels rank for clicks, not truth. Here's our attempt to do this honestly. Top 10, ranked, cited. Your kitchen is a museum of ancient chemistry. Every jar of pickles, every wedge of smoked cheese, every pot of honey in your cupboard is a working monument to a technique someone developed before germ theory existed, centuries before anyone understood what bacteria were. These people were not naive. They were working with mortal consequences. When the technique failed, people died. So the ones that survived did so because they happened to work on real chemistry. Water activity, pH, osmotic pressure, anaerobic conditions. We are ranking 10 of them, not by how old they are, but by how much the underlying science actually does. Number 1 made civilization portable. Before refrigeration, cold was the simplest tool available. Ancient Egyptians, Romans, and later medieval Europeans used underground chambers, natural springs, cool cellars to extend food life significantly. Romans are documented in ancient sources as importing snow and ice from mountains to cool food and drink, an expensive luxury that points to how valuable temperature control was understood to be. Root vegetables, stored well in earth cellars because cool, humid conditions dramatically slow microbial metabolism and enzymatic decay. Cold does not kill microbes. It puts them in slow motion. That distinction matters. Food removed from the cold resumes spoiling where it left off. The root cellar is still the correct answer for potatoes and apples. Command of. Keep them cool and dark, and most will last months, exactly as they have for several thousand years. The principle is unchanged. The cold is still doing the same work. Brig under the command of. Drying is among the oldest intentional preservation methods we can document. Archaeological evidence from the Middle East and surrounding regions indicates that sun drying of fish, fruits, and grains was practiced at least as far back as 12,000 BCE. The principle is simple. Virtually all microorganisms that spoil food require liquid water to grow. The amount of free water available for microbial use. Below roughly 0.6, most bacteria cannot reproduce. Below about 0.7, most molds stop. Sun-dried tomatoes, beef jerky, dried cod, raisins, dates, dried legumes all exploit this threshold. The mechanism is unchanged from the first person who noticed that fish left in hot sun lasted longer than fish left in shade. One thing the ancients did not know explicitly, but learned empirically slightly, too: moist, dried meat fails. Dozens of documented cases of explorer expeditions went wrong when provisions dried inadequately. Water activity, not visible dryness, is what matters. If cold removes heat and drying removes water, oil submersion works by removing oxygen. Submerging food in oil creates a physical barrier against aerobic bacteria, organisms that require oxygen to metabolize. Ancient Romans stored olives and cooked meats under rendered fat. The French confit technique. Cooking duck in its own fat and storing it submerged is a direct descendant of this logic. The technique works reliably for aerobic spoilage, and food stored this way can remain stable for weeks without refrigeration. The important caveat, which modern food safety knows, but ancient practitioners did not command of. Oil submersion creates anaerobic conditions, which is precisely the environment that Clostridium botulinum, the organism responsible for botulinum toxin, prefers. Modern safety guidelines for garlic preserved in oil require acidification for exactly this reason. The ancients, who made oil submersion work, were successfully eliminating aerobic microbes while avoiding anaerobic ones. Sometimes by luck, sometimes not. Smoking is a two-mechanism technique. It dehydrates food while simultaneously depositing antimicrobial compounds. Smoke contains phenolic molecules, guaiacol, syringal, and related compounds, produced by the thermal breakdown of lignin in the wood. These phenols are directly bactericidal and antifungal. The dehydration reduces water activity. The phenols attack microorganisms that remain. Neither effect alone is as durable as both together, under the command of, which is probably why the technique persisted, even when drying alone would have been simpler. Evidence of intentional smoking is prehistoric. Specific dates are difficult to pin down from the archaeological record, and we should be cautious about precise claims. What is documentable is that smoked fish and meat appear across archaeological records on multiple continents, that the technique remains in daily use: smoked salmon, smoked bacon, smoked paprika, smoked cheese. The phenols are still doing the same work they did around ancient fires. The chemistry is unchanged. Alcohol was probably not invented as a deliberate preservation strategy. It was discovered by accident multiple times in multiple cultures. Leave, grain, or fruit with sufficient water at the right temperature, and wild yeast converts sugars to ethanol. The earliest solid archaeological evidence for a fermented beverage is from the Jiahu site in China's Yellow River Valley, 7000 to 600 BCE. Residue analysis of pottery shards identified chemical markers consistent with a fermented mixture of rice, honey, command of, and fruit. Research published in the Proceedings of the National Academy of Sciences. The preservation value ethanol is toxic to most competing microorganisms. Wine and beer are hostile environments for pathogens. Under the command of. In ancient cities where water sources were routinely contaminated, fermented beverages were genuinely safer to drink. Alcohol-preserved fruit preparations extended the principle further. Still in use. Cherries, wine, preserved figs, and the fermented beverages themselves all work on the same toxicity that made the first accidental jar of Jiahu rice wine safer than the river it sat beside. The command of. Acetic acid, the molecule that makes vinegar sour, creates a chemical environment that most spoilage organisms and pathogens cannot survive. Threshold is pH below roughly 4.6. Clostridium botulinum cannot produce its toxin, and most spoilage bacteria are inhibited or killed outright. Vinegar production follows naturally from alcoholic fermentation. Acetic acid bacteria convert ethanol to acetic acid when oxygen is present. Command of. So cultures that had fermented beverages eventually had vinegar. Documented uses of vinegar for food preservation span ancient Middle Eastern and Chinese records. The Romans used vinegar extensively. Posca, a diluted vinegar drink, was a standard military field beverage. Pickled vegetables, fish preserved in vinegar brine, vinegar cured preparations. These appear across culinary traditions worldwide. The modern canning industry depends on measured acidity levels for shelf stability, under the command of. The vinegar on a commercial pickle jar label is the same chemical decision an anonymous preserver made several thousand years ago, now measured with a pH meter instead of a tongue. Sugar and salt work on the same principle, osmotic pressure. In high concentration sugar environments, water is drawn out of microbial cells through osmosis, preventing growth and reproduction. Preserving fruit with honey is documented in ancient Persian contexts, Mandov, and high sugar preservation appears across cultures wherever concentrated sweeteners were available. Candied, citrus peel, fruit preserves. These are not separate inventions. Command of. They are the same mechanism applied to different ingredients. The threshold for reliable preservation is high. Effective jam requires sugar concentrations around 60% or above, which is why underdone jam spoils. Still in daily use, and still working on exactly the same chemistry. One important historical note: before refined cane sugar became widely available in Europe in the post-Columbian period, honey was the primary high sugar preservative in Europe and the Near East, which means honey belongs higher on this list and explains why it is. Lacto-fermentation is not the same as vinegar pickling, though both produce sour, acidic food. The difference is mechanism in lacto-fermentation. Naturally occurring bacteria, lactobacillus strains present on the surface of vegetables, consume sugars in the food and produce lactic acid as a byproduct. The acid lowers pH. It also creates a competitive advantage for the lactic acid bacteria against pathogenic competitors. The result is a food chemically transformed by microbial ecology, not by an externally applied acid. Archaeological evidence suggests lacto-fermentation of vegetables was practiced in Mesopotamia by around 6,000 BCE. Pickled vegetables appear in documented Egyptian contexts. Sauerkraut, kimchi, naturally fermented dill pickles, brine, cured olives, fermented bean pastes across Asia, all lacto-fermented. The mechanism is ecological. You cultivate microorganisms that outcompete the dangerous ones. Nobody understood that mechanism explicitly until the late 19th century. Culpri. The technique was being used correctly for thousands of years before then. That is not magic. That is what survival selection looks like. Is the most chemically sophisticated natural preservative on this list and works via at least 3 distinct mechanisms simultaneously. First, water activity. Honey's moisture content is around 17% by weight, well below the threshold for microbial growth. Honey is mildly acidic, generally between pH 3.2 and 4.5, creating a hostile chemical environment for most pathogens. Third, and most unusual, honey contains the enzyme glucose oxidase. When honey contacts moisture, this enzyme generates gluconic acid and hydrogen peroxide. That continuous, low level hydrogen peroxide production means honey is actively and persistently antimicrobial in a way that salt and sugar simply are not. The consequence is well documented. Edible honey has been recovered from ancient Egyptian tombs, sealed for over 3,000 years without refrigeration or any modern intervention. Ancient Egyptians used honey in food preservation and in the mummification process under the command of, demonstrating an applied understanding of its properties that preceded any mechanistic explanation by millennia. Of, the enzyme mechanism responsible was not characterized until the 20th century. Of, salt is number one not because it is the oldest preservation technique. Drying and smoking are arguably older, but because of what happened when it scaled. The chemistry is osmosis. Dissolved sodium chloride draws water out of both food tissue and microbial cells. Command of, lowering water activity to levels that prevent spoilage for months or years. Applied to fish and meat, it converts a perishable protein into a stable, transportable commodity. By around 3000 BCE, Egyptian and Mesopotamian civilizations were salting fish at industrial scale. Roman trade networks depended on salted fish and on garum, a fermented fish sauce requiring salt, which was a traded commodity across the empire. The word salary derives from the Latin salarium, the command of. Connected to salt's economic centrality, though whether Roman soldiers were paid in salt directly or given an allowance to purchase it remains debated by historians. So take that one with a grain of it. In the medieval North Atlantic, salted cod and herring drove trade economics across entire regions. Salted provisions allowed ships to remain at sea for months, which made long, distance oceanic exploration logistically possible. Other technique on this list preserved food for households or villages. Salt preserved food at the scale of armies, fleets, and empires. The thesis of this video is that ancient chemistry is still in your kitchen. Command of. The thesis for this entry is that one piece of that chemistry changed the logistics of the world. Pull back. Your refrigerator contains every mechanism on this list. The pickles are acetic acid and osmotic pressure. The smoked salmon is phenols and dehydration. The honey is an enzyme making slow hydrogen peroxide. Command of. None of the people who invented these techniques knew the mechanism. They knew that people lived or died, and they kept doing what worked. The chemistry was always there. We mostly discovered it in the 19th and 20th centuries. The techniques are thousands of years older. If you'd rank these differently, the comments are open. Bring evidence. Until next time.